All right, today we're going to crack open the scientist's toolbox to tackle one of the biggest challenges in modern technology, getting our hands on rare earth elements. You know, they're the secret sauce in basically everything, from your smartphone to wind turbines, but finding them and getting them out of the ground, well, that's one of the toughest puzzles out there.
So, to really get a sense of what we're up against, let me ask you a quick question. What's harder than finding a needle in a haystack? We've all heard that one, right? It's the classic metaphor for a nearly impossible task.
Well, how about this for an answer? Try pulling a few specific, absolutely vital atoms out of a literal mountain of rock. I mean, that's the insane scale we're talking about here with rare earth elements. It's this incredible puzzle that needs a mastery of chemistry, physics, and you know what, even biology to solve it. And let's be clear, this isn't just some fun science experiment. It is absolutely essential for our tech-driven future. These elements are basically trapped in stone, and we desperately need the right keys to get them out, both efficiently and sustainably. Okay, so let's get into it with our first core concept, hydrometallurgy. It sounds super complex, I know, but the basic idea is actually pretty straightforward. It's the science of using liquids, usually water-based chemical solutions, to dissolve and pull out the specific metals you want from all that raw ore. This is really our foundational tool. So the first set of tools we're pulling out of this toolbox are what I like to call the chemical keys. These are the fundamental, tried-and-true methods that scientists use to unlock rare earth elements, or REEs, from the minerals that are holding them captive. Now, there are two main ways to go about this. On one side, you've got acid leaching. Think of this as the direct approach, almost like kicking down the front door. You use powerful acids to dissolve the REEs themselves. But then, on the other side, there's alkaline leaching. This is more of a strategic move, like finding a back window. You use a base to break down the rock around the REEs, which causes them to just fall out. Each approach has its own strengths, depending on the type of rock you're dealing with. So, what does this actually look like in practice? Well, first you have to prepare the ore. That means a lot of crushing and grinding. Then you apply your leaching agent, the acid or the alkaline solution. What you get is this liquid soup that's rich in REs, which you collect. And then comes the final, absolutely crucial step, purifying those elements out of the solution. And get this process can be remarkably efficient. A 2024 study by TN and colleagues showed that even when they were recycling the leaching liquid over and over again to make the whole process more sustainable, they could still hit a leaching efficiency of over 93%. That is a massive win for cutting down on waste.
Okay, but now we're going to move beyond just brute force chemistry. What's really exciting is that scientists are starting to look at nature's own toolkit, and they're finding some incredibly clever and much greener solutions for extraction.
I'd like you to meet the microscopic miners. Researchers like Wang and their colleagues have zeroed in on specific microbes, like a fungus called Aspergillus niger and a bacterium Acidiobacillus ferrooxidans, that are just fantastic at this job. They naturally pump out organic acids and perform chemical reactions that literally dissolve minerals, releasing the rare earths in a process called bioleaching. It's amazing.
And this is where it gets really, really smart. A 2024 study from Ansari and the team highlights this brilliant strategy where they use bacteria to generate acid from pyrite, which is a mineral that's often just waste rock. That very same acid then goes on to leach REEs from another waste source, coal ash. I mean, you're using one waste product to process another. It's industrial ecology at its absolute finest.
Okay, so we've got the chemical keys, and we've got nature's helpers. Next up, let's see what happens when we bring in some heavy-hitting physics. You could say that if chemistry provides the keys and biology offers a gentle touch, then physics provides the power-ups that can just supercharge the entire process. Just look at this chart. It tells the whole story. Based on data from Tariq and his colleagues, if you try to leach a rare earth element from untreated coal ash, you get back maybe 28%. Not great. But if you first zap that same ash with high-voltage electrical pulses, or HVEP, look what happens. The recovery skyrockets to 77%. Those pulses create these tiny little fractures in the material, which makes it way easier for the chemicals to get in and do their job. And it's not just electricity. Other studies are showing the incredible power of these physical assists. Brown's team found that using ultrasound can speed up leaching reactions by an unbelievable 11 to 24 times. And research from Lee and their team shows that microwaves can actually help us pull REEs out of really unconventional sources, like plant biomass.
Okay, but here's the thing. Before you even think about using chemicals, microbes, or these power-ups, there's a strategic step that can make all the difference. It's all about working smarter, not harder, by sorting the material first.
I mean, look at this comparison. If you just try to leach everything, you're processing tons and tons of worthless rock. Geologists call it gangu. You're just wasting expensive chemicals and creating a mountain of waste. But if you pre-treat the ore to concentrate the valuable minerals first, you end up using far fewer chemicals, you produce way less waste, and you achieve a much higher recovery of pure REEs. It's a total game changer.
And this isn't just theory. Here's a fantastic real-world example from a study this year. Researchers took regular old beach sand and they used a whole sequence of physical sorting methods, spiral separators, magnets, flotation, to concentrate a mineral called monazite, which carries the REEs. And the result? They ended up with a concentrate that was nearly 98% pure monazite. Now that is an incredibly rich starting material for the next chemical step.
And this sorting isn't just about big physical machines. You can do it with some really clever chemistry too. For example, a study by Clementin's team showed they could add something called oxalic acid to a mixed-up solution. And just like magic, it caused over 98% of the rare earths to selectively drop out as a solid, leaving all the impurities behind in the liquid.
Okay, so let's bring all these tools together. The future of rare earth extraction isn't about finding one perfect method. It's really about building a smarter, more integrated, more complete toolbox for whatever job is at hand.
Ultimately, there is no single magic bullet here. The most efficient, the most sustainable path forward is going to be combining all of these tools, starting with smart physical sorting, maybe adding a physical boost like HVEP, followed by a gentle bioleaching process, and finishing it all off with a targeted chemical purification step. It's all about creating a tailored, multi-stage strategy for each specific ore.
So we'll leave you with this thought. The scientific question has completely shifted. We know we can get these critical elements out of the ground. The real challenge now, the one that's going to define our technological future, is figuring out how we can do it in a way that is smart, efficient, and truly sustainable for our planet.